Okay, geometry, here we go. Our first section of the book here, 1.1, is just called the geometric system. And in this section, your authors are really just trying to give you a sense for how geometry works, trying to give you some basic building blocks you're going to need in order for things to make sense when we get to them here throughout the rest of chapter 1 and really the rest of the book. So we start off talking about something that sounds weird here. It's called the axiomatic system of geometry. So that word right there is based off of the word axiom, which we're going to get to in just a second. But they kind of try to break it down and try to show you that geometry works with one idea building upon another. We begin with some vocab right here, and we start off trying to define something called undefined terms, which is a little silly. We're trying to define something that is undefined. That's a little bit weird. But our simple definition here is that undefined terms in geometry are going to be easily understood concepts that are difficult or maybe even impossible to formally define. And this is actually what we're going to dive into in our next section, 1.2, a little bit further on. You don't really need to write these down here, guys, but the three basic undefined terms in geometry are a point and a line and a plane. Okay, so these are all kind of the basic building blocks of geometry here, and we do our best to try to explain them, but they're difficult terms. For example, a point is just something really, really basic in geometry. A point is basically just a dot, but it's so simple that there's nothing really substantial to put there as a definition to it. So that's what we mean by undefined terms. They're important, they matter, they exist, but they're almost so simple that it's difficult to put into words. A science example I always talk about is the concept of air, and trying to define what air is a pretty difficult thing because it's just so basic. But let's move on. Second thing we're going to do here's another odd one. We're going to try to define the word definition. That's a little meta. So a definition here within geometry is an explanation that assigns properties to a mathematical object. So obviously, since we're saying it's a mathematical object, our definition of a math definition is a little bit different than our definition might be, say, of the word definition in an English class or maybe a science class. But a couple of important things to note about definitions right here. First of all, definitions are true 100% of the time. That's why it's important that we write them very, very carefully. So sometimes geometry students get a little bit annoyed with their teachers because the definitions tend to be kind of wordy, and they say, why are you guys making this so complicated? And the answer is because our definitions need to be ironclad. They need to be true all of the time, and so we've got to word them very, very carefully. Another important thing right here is the concept that definitions are always reversible. For example, if we were to define here if I could spell, that'd be great. If we could define a triangle right here as a I'm really having a hard time spelling here, a three-sided polygon. And if that's a word you're not quite familiar with, don't worry, we're going to get to that later in the year. But if this is the definition of a triangle is a three-sided polygon, then you can also reverse that. And if I were to tell you that we are dealing with a three-sided polygon, you could then reverse that definition to say, aha, the thing that we are dealing with here must be a triangle. So you can work a definition in both ways. Another example for that might be something like if we were to say that Independence Day, we'd have to be careful here in America, if Independence Day is celebrated then on July 4th, that would be kind of the definition of it for us. You could reverse that and say that if we knew it was July 4th, if you started with that information, then you would know we're dealing with Independence Day. So definitions can go in both directions there. That's not going to be true for everything else that we talk about, including this guy right here. So here's that word that we used on the first slide here. Axiom was the root of the word axiomatic. So two words that are probably pretty new to you guys here. I wouldn't think these are things that you're familiar with coming into a geometry class, an axiom or a postulate. And these two words can be used pretty much interchangeably here. They mean a statement that is accepted as true without proof. So that's an important concept here, and we really don't like to do that very much in geometry or any level of math or science. But again, there are certain things that are so basic that every person with a little bit of critical thought can look at one of these statements and understand that the statement has to be true, even though it's really, really difficult to explain why. So for example, one of the most basic postulates of geometry that was given to us by an ancient Greek mathematician named Euclid, who lived, I should know this and I don't, but I do believe it was several hundred years BC. One of Euclid's basic postulates of geometry is through any two distinct points, there is exactly, and I left this one blank. And if we thought about what that means, well, here would be one point, and we'll call that point A. And through another point over here, it's got to be separate from the first one. That's what the word distinct means. So here you go. Through any two distinct points, what could we draw, everybody? Well, Euclid's most basic postulate says that between points A and point B, you can draw one and only one line. So that is one of the basic postulates of geometry. Through any two distinct points, there is exactly one line. I can't draw a different line that passes through points A and B. If I tried, let me switch to green right here, I'd have to break something. For example, some people say, okay, look, there's a line, and that passes through A and B. Well, no, that's not a line. As we're going to define in section 1.2, a line needs to be straight. And what I drew there in green was a curve, so that doesn't really do it. And if you tried to draw any other straight line between A and B, you would really just end up drawing the same line that we had there just a second ago. So, if I were to ask you guys, do you accept this statement as true? Through any two distinct points, you can only draw one unique line. Most people are going to say, yeah, that's true. And they're going to think that it's relatively obvious. And if I were to ask you then, how do you know that's true? Well, that's where things get a little bit more difficult. It's hard to give a reason for that because it's kind of self-evident. And that's very often what happens when we are dealing with something called an axiom or a postulate. It's something that we know is true, but it can't really be formally proven. So it's kind of like talking to a little kid, and when they always ask the question of why is this the case, why this and why that, and at some point you just have to say, because it is. And to some extent, that's what we do in math here with what we call postulates. All right, what's the next term we need to define here? That would be a theorem. And again, like an axiom or a postulate, I wouldn't think you guys necessarily know what a theorem is. It's an important thing we talk about in geometry, although you probably know at least one mathematical theorem by name, even if you can't think of it right now. So a theorem is a statement or a conjecture, and a conjecture is a funny word too, but that basically just means it's a type of mathematical statement. So a theorem is a statement that can be proven true. That's important right there. That can be proven true using undefined terms, definitions, and axioms or postulates. So, the big difference between these last two slides right here, an axiom or a postulate we know is true, but we accept it without proof. However, a theorem, we know that it's going to be true, but this one can be proven, or more likely has been proven, using these three building blocks that we talked about: undefined terms, definitions, and axioms or postulates. Now, probably the single most famous theorem in mathematics is written right here in the example we've typed out. In a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. And if that sounds familiar at all, guys, hopefully it does, that has a fancy name right here called the Pythagorean theorem. And that one is the Pythagorean theorem and not the Pythagorean axiom or the Pythagorean postulate, because it can be proven true using some of these tricks that we talked about. And I'm not going to bore you guys too much right here with the concept at work right here, but using some things that we're going to talk about later on in the year here, if we had a right triangle, that wasn't drawn very well, and I called this leg A and this leg B and this leg, this hypotenuse down here on the bottom, one of the things we're going to learn later on this year is if you drop what's called an alpha altitude straight down here to that side. And if I called that H, and this piece right here I'd call X, and this piece right here I would call Y. Let's see, you guys are going to learn a couple of theorems right here that basically kind of relate a lot of the side lengths within this triangle right here. And I tell you what, I'm not going to go through it right now. I don't think it'll mean much to you, but there is a way to prove that the Pythagorean theorem actually works out. In fact, there are multiple ways of proving it. So a lot of different mathematicians have submitted their own unique proofs of the Pythagorean theorem, and they all reach the same conclusion, that in any right triangle, one of your legs squared plus your other leg squared has to equal the square of the hypotenuse. And that's the Pythagorean theorem, which I'm guessing you guys have seen at least once before in math, if not more often than that. So that's the difference between a postulate or an axiom and a theorem. Postulates, we simply accept that they're true without proof, but with a theorem, it can be and it has been proven true. Okay, getting towards the end, this is a relatively short section right here. Your author also introduces in this section different types of geometry, and they really just focus on two that we're going to be talking about this year. The first one is called synthetic geometry, or Euclidean. So there's that name, Euclid, that I talked about just a little while ago, that famous Greek mathematician. So synthetic, of course, kind of means made up. So that is the study of geometric figures without the use of coordinates. Basically, just trying to make this easier for you guys to understand, when we freehand a diagram, that's usually synthetic or Euclidean geometry. So if I were to ask you guys to draw a square below, hey, any first grader can tell me what a square looks like, right? 4 sides, and it does something like this. And of course, the definition's maybe a little bit more complicated than that, but most of you guys would probably draw that for me. And if we wanted to be thorough, I'm getting into a little bit of what we're going to do later on in the year, we would want to label all of these points, point A and B and C and D. And if we wanted to be really thorough, we would know that in a square, your 4 sides have to be, the geometry word we use is congruent, which means equal length. So I would use these little red tick marks right there to show that all 4 of those sides are the same. Furthermore, a square also has to have 4 90-degree angles. So I would put right angles in all of the corners right here, and that's an example of how we would kind of freehand draw a square. You'll notice I didn't use anything to help me there. I didn't use a ruler, and I certainly didn't use what we're going to talk about on the next and last slide, which is a coordinate system. So that was A, synthetic geometry or Euclidean geometry. Now the second thing we're going to talk about in B is called analytic geometry. And this one is sometimes also called Cartesian geometry, named after a famous mathematician named René Descartes. There you go. So that C-A-R-T in the middle of Descartes' name is where Cartesian geometry comes from. And that is defined as the study of geometry using a coordinate system. So, in an example of Cartesian geometry or analytic geometry, if I were to ask you to draw and label a square below, I would choose some random point on the coordinate plane, and I'm going to pick this guy right over here, and I'm going to call that point A. And now I'm going to try to just be a little bit more careful than I was last time about creating my square. So what I think I'm going to do here is choose a random number, and I think I'm going to pick 5. How about that? I'm going to go 5 units up from point A. 1, 2, 3, 4, 5 gets me right here, and that's going to be point B. And then I'm going to go to the right now of point B, and of course I need to go how many units? 5, the same unit to the right that I just went up from A to B. 1, 2, 3, 4, 5, right over here then would get me to point C. And then to locate point D, we're going to go 5 units down and get point D right over here. And now, if I were to actually connect those points, and ideally I'd be using a ruler here, but I think you guys get the point, now we have a square that was more carefully drawn than just freehanding it like I did on the last slide. And you could go even further. We could label the coordinates here. It looks like point A. Remember, guys, that we always do coordinates based on the origin right here. So to get to point A, we went 4 units to the left, and then we went 2 units down. So the coordinates of A are going to be -4, -2. Yeah, I guess I did that in blue. Okay, there you go. And let me just do this real quick. Let's do the coordinates of the 3 other points here as well. So point B, again, from the origin, we're still going 4 units left, but now we're going 3 units up. So -4 for our x-coordinate and 3 for our y-coordinate. Point C, located right here, again, starting at the origin, we're going 1 right and up 3. So that's 1, 3. And then again, one last time now, from the origin to get to point D, 1 to the right and down 2. So that's a 1 and a -2. So that's what it would look like to draw a square using analytic or Cartesian geometry, where we're just a little bit more formal there about our coordinates. All right, guys, that's really everything I think we needed to cover here in section 1.1. And then once we move on into the next section, we're going to use some of these tools and build upon them in order to get a better understanding of some of those basic building blocks in geometry.